morning, ladies and gentlemen. We're going to do kind of a precursor to Chapter 9. Our objectives are that we're going to review definitions and formulas from our sequences and series that we did a couple of years ago in Pre-Calc. So most of today is just a lot of definition and formulas, because yes, it's a lot of writing, but I think it's important that we go back over some of this stuff. All right, so just to make sure that we get all of our definitions in, a sequence is a collection of numbers that are listed in order. So we're going to get a crash course of the entire Chapter 9, almost the entire chapter, on sequences and series from Pre-Calc. An infinite sequence is just a sequence that goes on forever, okay? So I'm just going to write goes forever. It's going to be highly technical. All right, a finite sequence, on the other hand, does not go on forever, and it has a definite beginning and end. All right. Let's talk about some notation. In sequences and series, n is going to represent the position of the term. So for example, if I had numbers, or if I had a sequence that was M, T, W, T, F, S, S, this particular term would have an n value of 3. This particular term would have an n value of 7. And in case you didn't figure it out, it's the days of the week. Alrighty? And then a sub n would be the specific term in our sequences. So if I did a sub 3, that would be W. And if I did a sub 7, that would be the second S, okay? We also talk about, in sequences, we talk about a rule. And a rule is a formula to generate the terms of the sequence. And I am going to go back and show you eventually, as we're doing things, like right away, how to do this in your calculator, because your calculator can generate all the terms for you. So an example of a rule would be a sub n is 3n minus 2, all right? Or maybe another one is 3 plus a negative 1 raised to the n, okay? And so that would be that. Alrighty, so let me actually go ahead and bring in my calculator. Sorry, one of these days I'll stop coughing. And so I want to bring it in. And I don't know that I can bring it in and write at the same time, but I'll try to get the crap out of the way. Alrighty, give myself a little bit of real estate with paper. So if I turn on my handy-dandy grapher and clear everything, the first thing that I would do is go to my mode button, and I'm going to put my calculator in sequence mode, okay? Then I'm going to quit, and then I go to my y equals, and notice that this is the screen that you see. So the n min is where is the sequence starting. So n min is always going to equal where does my sequence start, okay? And remember, oftentimes when we were in Pre-Calc, you could start with a 0 term, which is often like an initial investment, okay? If I buy a car, the cost of the car is the initial investment. When I get to the 1 in the sequence, that would be my first month's car payment, okay? But hopefully you're paying off a car very quickly and not carrying debt. The UN right here then would be the rule. So my U of n is going to equal the rule, and we'll enter some of those in just a moment, okay? And then this one right here, the next one, it's the third line. It takes 3 lines for every sequence. This is actually the value of whatever you entered in the first line. So first line's term. And I guess if I were doing appropriate grammar, I'd put that guy in there, okay? So the third line is always, come back calculator, is always going to be the value of what you entered on the first line, okay? So let me show you another trick. So I'm just going to enter one of the rules that I had written. I'm actually going to enter the one that's under my calculator because it's a little bit more entertaining. So I'm going to start that sequence on n is equal to 1. And it was 3n. Remember, on your variable button, n is the variable when we're talking about sequences. And again, n represents the number's position in the sequence. And then if I entered the -2, okay, and then I need to enter the value of the first term of the sequence. So 3 minus 2 is 1, so I'm going to enter a 1. So now I have the beginning information for my sequence. So I'm going to quit, and I'm going to go second, this U that's above your 7, which you can't see because my finger's in the way, and then I'm going to do 1, 5, close parentheses, and my calculator will generate the first 5 terms of the sequence. Well, let's say I wanted to do the same sequence, and I wanted to go from the 10th term to the 15th term, okay? Well, there is, I think that's good grammar, there is the 10th term through the 15th term. So your calculator will do a lot of work for you in a sequence. Alrighty. The next thing that we need to talk about is summation notation. But since you've been in calculus now, I don't think this is quite as scary as it was when you were in pre-calc. So my summation notation is just going to be what you're used to seeing, I equals 1 to n. Notice that I'm talking about the nth term of the sequence, and then I would have my rule to determine how I'm going to generate the sequence, okay? So this is, I want to sum from the first term to the nth term of whatever this would be. So then what if I had one that said k is equal to 3 to 6? So I want to sum the terms 3 to 6, and if I had 1 plus k squared, this is the rule, then this would be the sum of the terms from 3 to 6. Okay? If I did it by hand, it would be 1 plus 3 squared, and then I would have 1 plus 4 squared. And notice that our n's are integers. N is an integer. I guess I should have said that in the past. But I'm not going to increase by a partial number because I'm going in consecutive terms of the sequence. So n is always an integer. And then 1 plus 5 squared and 1 plus 6 squared. So if you did all that math by hand, you would get 90. Well, that's annoying. So instead, I'm going to bring in, I have to put it over here, otherwise the glare is really bad. If I bring in my handy dandy grapher, and I go to my math button, and I go down a ways, there it is, there's my summation button, okay? And notice it's just like entering a derivative or an integral, so I'm going to say x or n, and that's okay, 3, and then I'm going to go up here to the 6, and then I have to put in my rule, 1 plus n squared, and I don't actually have to be in sequence mode to pull that off, but I didn't change the mode on my calculator, so it really doesn't matter what the variable is. I push buttons, and then I get 90, and there's the sum of your sequence. So it is, if you have the opportunity to use your grapher, it's always way easier to do it in your grapher. All right. The next definition, we'll change colors, at least we can get some color in here, is what's called a series, okay? So currently we've talked about a sequence, which is a collection of numbers. Well, a series is a partial or whole sum of a sequence. So I can start anywhere within a sequence and do a sum, or I could sum the whole sequence, okay? If I'm doing a partial, this would be a finite series, meaning it has a specific beginning and end. And if I'm doing a whole, this would be an infinite series, because in theory, a series goes on, or a sequence goes on, forever and ever and ever, okay? if I'm given summation notation, so let's use this one, I equals 1 to 6, and then maybe our rule is 3i minus 1, okay, this says I want to sum the first 6 terms of the sequence, right? And again, I could do that in my grapher, or I could do it by hand, and I would get 57. So this would be a finite series because I am summing a specific amount of terms. It's always important to know how many terms are being summed, and the how many, I'll give you a variable for it in a little bit, is going to equal the top minus the bottom plus 1. Okay, so in this particular case, if I do 6 minus 1, I get 5, but I have to add 1 to make sure that I include both end points, and so it's the top minus the bottom plus 1. So in this particular case, I would be summing 6 terms. All right, so now that pen's really kind of ugly. Let's switch to a different one. Let's talk about some formulas for sequences. So we're going to kind of jump back and go talk about sequences, okay? In pre-calc, we talked about there are 2 types of formulas. One is a recursive formula, and if you'll remember, this means that the formula is in terms of the previous term. And it's going to look something like this. U sub n, doesn't matter what the variable is equal to u sub n minus 1, the previous term, and then maybe plus d. Okay, and we'll talk about what d represents in a minute. On the other hand, I can have an explicit formula. An explicit formula is in terms of a number's position. So remember that n represents the position of the number. So an explicit formula is in terms of the number's position. And maybe that formula looks something like it's going to be the first term plus the position minus 1 times d. Okay? So notice the difference in the 2 formulas. In this formula, here is the number's position. And then in this formula, it says use the previous term and add something to it, okay? So the next thing we want to talk about are a couple of different types of sequences. The first one that we're going to talk about, I'll scoot my paper down just a sec, is an arithmetic sequence. Okay, I can scribble that out. So an arithmetic sequence says that the differences between terms are the same. So that means that I either add or subtract the same value to every term in the sequence, okay? And if I needed to figure that out, if it wasn't told to me, and I'm going to restate the obvious, but I would do new brain and mouth, new minus old, right? And so if I were talking about sequence numbers, it might be a sub 3 minus a sub 2. Can't skip terms, because then you have to divide by how many terms you skipped. All right, and again, I have 2 ways of writing formulas for an arithmetic sequence. I can write an explicit formula, and that would be kind of the one that I've already written, but just in case you didn't know that. Okay, all right, so here's the explicit formula. And this explicit formula says use the first term in the sequence, or wherever we're starting, plus the term's position, minus 1 times d, and d is called the common difference. And again, I can find that if it's not given by doing new minus old. The recursive formula, on the other hand, is in terms of the previous term, and it would look something like a sub n is equal to the previous term plus the common difference. So if you notice, the differences in between the 2, okay, so this says take the previous term, so I have to know the previous term, and then add a value. This one is actually y equals my mx plus b, because here's my variable, right? Here's the slope, and then this would be the y-intercept, or the first term. So speaking of that, you can actually graph sequences in your calculator, which we will use later in the calculus part of this. It will be really handy. And if you graphed a sequence from point A to point B, it is an individual, this is not arithmetic, by the way, it would be an individual collection of dots, and each dot would represent an individual term in the sequence, okay? This is not arithmetic, by the way, because an arithmetic sequence would be linear, so that's a my bad on the example. All right. So let's just do an example and get some entertainment in. So an example of this would be, sorry, one of these days that's going to go away. The fourth term of an arithmetic sequence, it's nice that they tell us what type of sequence we're dealing with, is 20. And then the 13th term is 65. So they want us to write the first 5 terms of the sequence. Okay. So we need to write down information that we've been given, because it's always important to know what you're working with. So I know that a sub 4 is equal to 20, and I know that a sub 13 is equal to 65. Okay? So the difference between these two guys is 9. There's 9 terms in between, because that's really hard math. So I know that a sub 13 is going to equal a sub 4 plus 9 times the common difference, because from 4 to 13 is 9 terms away. So then I get 65 is 20 plus 9d. I solve for d, and I get that my common difference is 5. So I needed to be able to find the common difference before I write the model. Okay, I'm going to write an explicit model. So I'm going to write a sub n is equal to a sub 1 plus your common difference times n minus 1. Okay, I don't know the first term, but I can find it. So I'm going to do some more math. So I'm going to say a sub 4, I just picked one, is equal to the first term, my common difference, and then this number's position is 4, and I'm going to I'm going to substitute this in. So 20 is equal to a sub 1 plus minus 1, sorry, bad math, 9 times 3, and so then I get that the first term is equal to, I did some bad math. Yep, there it is. I was going to say, what the heck am I doing? Whew, it's a good thing. There we go. And now I get that my a sub 1 is equal to, when I solve for a sub 1, because 20 minus 15 is 5. Well, now I can put that handy dandy grapher equation into my grapher. So I'm going to say a sub n is equal to, let me scoot this up so you can see, my a sub 1, which is 5, plus the common difference, which is 5, times n minus 1. And I'll bring my calculator in and put that handy dandy equation in. So I'm going to go back to my y equals, and I'm going to enter my 5 plus 5 times n minus 1. My first term was 5, okay, alrighty, and then I'm going to quit, and I'm actually going to do, they wanted the first 5 terms, okay, so now there's my first 5 terms. Woohoo! That was pretty easy, right? And you could have gotten the 5 terms quite easily by hand, but sometimes it's nice to be able to see it done in your calculator. All right. So the next thing we want to talk about while we're in our arithmetic sequence is talking about the sum of a finite, which means I want a definite number of terms, arithmetic sequence. Alrighty, so here we go. I can start anywhere in the sequence. I can end anywhere in the sequence. So the notation would look like I'm going to sum from I equals 1 to n, and then I would have some rule and then I would do a summation. Well, I don't have to do the summation because I have a handy-dandy formula that says the sum of a specific number of terms. This is where the n gets a little bit crazy. This is saying how many to be summed. So I think that's why sometimes we get confused with sequences and series, because sometimes our n's mean different things. And then the formula says it's the number of terms divided by 2, the first term and the last term. So again, for whatever reason, mathematicians chose to use variables, and it seems like it's a little confusing. So this says how many terms are being summed. This says here's the number of terms being summed divided by 2, first term, last term. Okay? So then I would put that into my handy-dandy grapher, and then I would be good. Okay, so let me switch to another piece of paper. If I were to do an example with this, let's say it said find the 150th partial sum, which means I want to sum the first 150 terms of the arithmetic sequence, and we're halfway done, by the way. Lots of definitions today. And I'm going to have 5, 16, 27, 38, 49. Alrighty? So instead of trying to generate that 150th term by hand, we're going to write a rule. Okay, so I can figure out that my common difference, 16 minus 5 is 11, 27 minus 16 is 11, 38 minus 27 is 11. The common difference has to be the same for all terms. So I know that my D is 11. So my explicit formula, it doesn't matter whether you write an explicit or a recursive, but in a recursive, I don't know necessarily the previous. And actually, I'll show you how to enter the recursive formula in your calculator. But this is going to say this term is equal to the first term plus this times that. Okay? And so if I find my first term, it's 5, right? There's the plus. I have a, what did I do? N minus 1 is the variable. Whew, there we go. Having a brain fart there. So then I would put that in my calculator. And then I would do U of 150 in the main screen, and that would tell me that my 150th term is 1644. Okay? Let me show you how to enter the recursive. So the recursive formula says that U sub n is equal to the previous term plus the common difference. Okay? So if I want to enter that in my calculator instead, because I do know everything, so I would write U sub n is the previous term plus 11. Okay? So if I go back to my handy-dandy grapher, and again, notice I would start at the first term. I'm going to clear this guy, and I would enter my U, and then I would do n minus 1, and then plus 11, and I know that my first term is still 5, second quit, and then I do second U of 150, and there's my term. So it really doesn't matter whether you do explicit or recursive, you're going to get to the same place. I don't know the previous term, but if I put the rule in my calculator and I tell it what the first term is, then it does all that fun math for me. All right, we're still looking for the 150th sum. So the sum is the number of terms divided by 2, first and last. Okay. Well, now, if I'm doing the 150th partial sum, I'm summing 150 terms, okay, because 150 minus 1 is 149, plus 1 is 150, divided by 2. The first term is 5. The last term is 1644. And then when I do that math in my handy-dandy grapher, I get that the sum is 123,675. Okay? All right. So let's do another little example while we're still talking about arithmetic sequences. And this one says, find the sum of the first 100 positive odd integers. Well, that's cool, right? So that means we would do 1, 3, 5, 7, dot, dot, dot. Okay? So my common difference is 2, pretty easy. And I'm going to write a recursive formula. So my u sub n is going to be u to the n minus 1 plus my common difference. Here's the variable, n minus 1. My common difference is 2. We do qualify this by saying that n has to be greater than or equal to 2, because if you notice, if I put a 2 in here, 2 minus 1 is 1, which tells me that I'm starting at the first term, okay? I would put this rule in my calculator because I need to have the 100th term. Well, if I do that, if I find a sub 100, did I show that in my math? I did. So a sub 100 or u sub 100, sorry, I flip-flop variables, no significance, would equal 199. And again, I would enter this in my calculator. I would find the 100th term, and then I'm just going to do my handy-dandy formula, which just says that S sub n is n over 2, that's a 2, a sub 1, a sub n. Well, I'm summing the first 100 terms divided by 2. First term was 1, last term was 199. Do that math in my calculator, and I get 10,000. So the sum of the first 100 positive odd integers is 10,000. If I wanted to report it very nicely, I would write it like that. So now we're going to switch, and we're going to talk about a geometric sequence. So we just spent some time talking and working with arithmetic. Now we're going to talk about geometric. All right, so this one says the ratios, and anytime I have a ratio, I am multiplying or dividing, notice I'm too lazy to write the words, of consecutive terms are the same. So kind of like with our arithmetic sequence, so now instead of adding and subtracting a same value, I'm multiplying or dividing by the same value. If I need to find that value and it's not given, R is going to be new divided by old. So if I put it in sequence notation, R would equal the next term divided by the previous term. Okay? Alrighty. The formula, the recursive formula, is going to equal a sub n is equal to the first term a sub 1 times r, guess I don't need that parentheses, raised to the n minus 1. So remember, r is going to be my common ratio. A sub 1 is the first term, and n is the number's position. Okay? So if we start with an example, then I want to find the 15th term of the geometric sequence. And again, unless I'm told to do this by hand, I never do it by hand. Okay, and the sequence that we're going to be given, nice and polite, 5, 15, 45, dot, dot, dot. Okay, so if I do new divided by old, I get that my r is 3, my a sub 1 is 5. And I do tend to switch back and forth between u's and a's because your calculator has u's and some books use a, so it really doesn't matter, and I apologize, but I tend to forget and just flip back and forth between u's and a's. Alrighty, so then I'm just going to write my handy-dandy formula, and I would write a sub n is a sub 1 times r raised to the n minus 1. So my formula, and I would put this in my grapher, my first term is 5, my r is 3, and then, actually I'll put parentheses in. If it were me, I would put that rule in my calculator, and then I would do a of 15, and then I would get a really big number, so it's 2, 3, 9, 1, 4, 8, 4, 5, 1, 2. Ta-da! All right, so obviously it's easy to tell that a geometric sequence is going to grow really quickly. All right, so we know how to write a recursive formula for geometric, so now we have to sum. So I want to talk about the sum of a finite, has a definite beginning and end, geometric sequence. Okay, and we're going to be doing less writing, I think, of the rules, but more about generating the terms from a calculus perspective. I think that's true. All right, so the sum is going to equal the sum from I equals 1 to n of a sub 1 times r raised to the n minus 1. But again, I don't necessarily want to do this. I want to have a handy-dandy formula. And my formula is going to be the first term times 1 minus r raised to the n over 1 minus r. And then that would be my handy-dandy little formula. Okay? So, yes, I could put this into my calculator, and I could do the math in my calculator, but if it's a no calculator portion of a test, you would need to be able to pull this off, okay, at least to be able to set it up. So let's say, for an example, I want to find, that's a D, the sum from I equals 1 to 12. So remember, I'm going to be summing 12 terms of 4 times the 0.3 to the I minus 1. So the way this particular problem is written, this is the first term. Sometimes it's not. So if I'm doing a sum that starts maybe on the 10th term instead of the first term, the 10th term wouldn't be 4. I would have to substitute the 10 in, run that math to find the first term, and then I would be able to finish the problem. Okay? But this one starts at the first term, so it's 4. So, yes, I could put this in my calculator and get an answer, but we're going to do it by hand. So it's going to be, and I'm not going to rewrite this since it's right up top, a 4. My common ratio is the 0.3, so it's 1 minus 0.3 raised to the 12 over 1 minus 0.3, okay? And then I would do that handy-dandy math, and I would get that the sum is 5.714, okay? So then I would say that the 12th sum is equal to 5.714, approximately equal to, okay? All right, there is a slight variation of this particular formula, and I'm just going to give it to you in case you ever see it. And it says that S sub n is equal to the sum from I equals 1 to n of a sub 1 r raised to the I. And if I have this problem, which is more of an explicit formula instead of this one, then my summation formula would become a sub 1 times r times 1 minus r to the n over 1 minus r. Okay? So virtually the same problem, but a little bit different. So this is the sum of a finite. Well, with a geometric sequence, we can also talk about, I was thinking about how I'm going to graph that. So let's say I graph this guy, and I want to sum my sum of an infinite, oops, spelled it wrong, I-N-F-I-N-I-T-E, an infinite geometric series. And remember, series means sum, sequence means collection. So we don't have this for an arithmetic, but we do have it for a geometric. We do have some qualifiers, though. On this one, the absolute value of r has to be less than 1, okay? If the absolute value of r is greater than or equal to 1, then there's no sum. No sum of the infinite geometric, you have all those math symbols, series, okay? If r is less than 1, then we would say my infinite sum, infinite, is equal to the sum from I equals 0 or 1 to infinity of a sub 1 r raised to the I is going to equal the first term divided by 1 minus r. So it's a really simple formula. And remember that the only qualification is that the absolute value, so it doesn't matter whether it's increasing or decreasing, the absolute value has to be less than 1. Okay? So if I do an example, and this one says find the sum from n is equal to 0 to infinity of 4 times 0.6 to the n, okay? Well, again, just to show you that the first term, okay, so if I'm starting at 0 instead of at 1, if I substitute a 0 in here, then I get 0.6 to the 0, which is 1, so my first term, a sub 1, is 4. Okay? We can assume that from the rule, but just in case we don't realize that, we can make sure that we do this. The formula says that the infinite sum is the first term divided by 1 minus r. Our r is less than 1, so we're good to go. This is 4 over 1 minus 0.6, and when I do that math, I get that the infinite sum is 10. Okay, and I know that sounds a little bit weird, but the infinite sum is 10. It's a little bit hurty on the head to think about an infinite sum. Okay, alrighty. I have one more example of this that I want to do just because it's a slightly different problem. So let's say I have the sum from n is equal to 0 to 50 of 10 times 2/3 raised to the n minus 1. Okay, so because this is a partial sum, okay, so I get to use the formula a sub 1 times 1 minus r raised to the n over 1 minus r, I need the first term. But notice what happens when I substitute 0, because this sequence starts at 0. When I substitute a 0 in here, I get 10 times 2/3 to the negative 1, which is 10 times 3 divided by 2. So my first term is actually 15. So this is when this particular situation can be a little bit deceiving, but it's always a good idea just to check and verify. The math is usually super simple. So then I know that if I want to do my summation now, so the sum, and I'm summing 50 minus 0 is 50 plus 1. I am summing 51 terms is going to equal my first term times 1 minus 2/3 raised to the 51, okay, not just the 2/3, I guess I should use a parentheses to make it look better, divided by 1 minus 2/3. And then if I do that math, which I am incapable of doing by hand, I would get that S of 51 is equal to 45. So sometimes with sequences in series, they do like to mess with your head and throw in some unique problems. And we actually have one more example, and we are done. I know this is a long video, but we needed to kind of set the stage. All right, so let's do the problem a little bit differently. Same basic problem, but I'm going to sum from n equals 10 to 50, and I'm going to have 10 2/3 raised to the n minus 1. Okay, but notice this time I'm starting to sum at n is equal to 10, so I still need to find my first term. So my a sub 1 is going to equal 10 times 2/3 raised to the 10 minus 1. Okay, and if I do that math in my handy dandy grapher, I get 0.2601. Not sure why I wrote it in 4 decimal places, but I did. Okay. So then if I want to do my sum, my summation says that it's the first term times 1 minus r raised to the n over 1 minus r. Let's talk about our n. 50 minus 10 is 40, plus 1. I am summing 41 terms, so then this is 0.2601. 1 minus my r is 2/3 raised to the 41, that's kind of weird, over 1 minus, oops, I forgot that. And then I can do that handy dandy math in my grapher, and I would get that my 41st sum is 0.7803. And again, I'm not sure why I chose to write 4 decimal places, but there you have it. Alrighty, you need to make sure that you highlight the formulas that we have used today. For geometric, it was an infinite and a finite. For arithmetic, it was a finite. And then you also need to think about your recursive and explicit formulas. Alrighty, that's it for today.